if you will not go in the presentation mode, then it will be okay. Everybody will see what you're showing.
Okay, so let me put everything smaller so I use better the space of the screen. So there?
Yes.
Yes, sir, it's visible.
Okay, still is not the best way to present it. So, oh, okay. I
We can read,
know.
sir.
Sorry.
It is visible and readable. We
Yeah,
can
yeah,
read what
but
is there.
when I know. Sorry, I know what I need to do. Okay, let's use this, although it's not the best because I will need to jump through slides. Okay. Okay, let's continue. So these are the. Let me see if I can increase the size here so you can see it better. Okay. Okay, so I was saying that this taxonomy has also a horizontal dimension that is mine. So I divide the problems of big data in three columns. These are data issues, computing issue, and the human issue. So the ones that I will cover today are the ones in red, but you can see that there are many other issues that are important in the different boxes. For example, veracity, a computing issue will be reliability and trust. For example, in the case of variety, basically you have very heterogeneous type of data, you have adaptability and extensibility, and so on. So I will cover mainly the ones in red. I think these are the most important challenges that we have today. Now, so let's very quickly talk about machine learning. So I will assume that you know machine learning, and basically the success of machine learning in the last, say, 10 years have been that you have more data, and that's big data. You have more processing power, GPUs, and also you have deep learning, which are not old, which are not new, they are old, like they are from the 60s, but now we have the capacity of build really many layers on these neural networks, and then we can do much better. In this case, we're using a supervised learning model that is shown here. And in the classical supervised learning model, as you might know, you have labeled data. So you have labels associated to data. You produce some feature vectors. In the case of deep learning, the neural network will find these features. So there will be this distributed representation. And then you learn some model, the predictive model that is here. And then when you have a new object that you want to predict, you get the same feature vector. In the case of the deep learning model, that will come together with the model. And then you get the expected label. Of course, you will have to cross your fingers because this is not time. We hope that works, say, 90% of the time. And there are many applications of this, like share economy, driverless cars, important if you are doing predictions. So let's say we have an axis of complexity. So this is the complexity of the problem here in the left. And then you have the size of the data, the volume of data in the right, in the x-axis. So if you want to build a classifier that recognizes my face and translates this to my name, this is not so difficult. But very important, you are only changing the representation of the data. So instead of having an image, you have now a word that is my name. But still the system doesn't understand what implies a name. So it's a syntactic transformation. It's not a semantic transformation. And very important that. Now let's imagine that you already know the main equation that Einstein discovered, that energy is the mass times the square of the speed of light. Well, that applies to any data, to any object in the world. So basically, you can think that this is like, it's after Einstein finds it, it's very easy. There's no complex. You just use the formula, and that applies to any volume of objects in the future. And now you may have something more complicated, where you have some size, but doesn't matter how much. Is, for example, the stock market. The stock market is very difficult to predict. Why? Because it's not rational. So there's a lot of irrational behavior. And imagine that you could predict the stock market, then the stock market will not exist, because it will not make any sense to have something that all the people can predict. It will be almost impossible to obtain money there. And then there are other problems that are complex, where you need much more data to learn. Here, it doesn't matter how much data you try to put, you will not learn more because it's irrational. So it's more randomized. This is, in some sense, this is a position about predictability. And then you can have something much more complex, like the Garden of the Lights. This is a famous painting from a Dutch painter that has a lot of animals, but the animals are in very strange shapes. So to learn which animals you need to recognize will be very hard. So the question, the task here will be, try to recognize all the animals in the pictures, but using, for example, the standard animals. That will be much harder. So it's important to understand that predictability depends not only on the amount of data, but also depends on the complexity of the problem. And there are some problems that basically will be very hard to predict, like the stock market. Now, which are other opportunities? I already mentioned some industry that use this, but now we can think that we have truly data-driven decisions. You can do global optimizations. Typically, we were doing local optimizations, and now you can do global optimization because these systems can capture much more data. You can not only learn in a way that the machines learn, not in the way that humans learn. You can predict, but also more important, you can prescribe. So you can try to do things before things happen if you're predicting right. For example, if you predict that the machine will fail in the next month, then you can, for example, send that machine to maintenance to make sure that it doesn't fail. You can use all your personal data for your well-being. For example, you have here personalized medicine, trying to help you day by day using your mobile phone, etc. Of course, other people is also using your personal data to predict other things, to give you advertising, which are not so nice. But I guess it's part of what we have to pay to get a lot of free services like search, like mail, like many other things. But we need to have some red line in data privacy, and this is happening these days when Apple started to no tracking, when cookies will disappear in the near future, and so on. So we are moving towards more data protection in the future. And finally, the most complicated opportunity is machines deciding for us, what is called automated decision making. And this is like interesting, but also has ethical concerns, and I will be something I will talk at the end, because in many cases we don't want to have machines deciding for us, and also even when we want to, we shouldn't want to do it because it's not ethical. So whenever you use big data, you need to ask the right questions. And these are the questions that basically are behind all the challenges I will present next. So first, you need to be problem-driven, not data-driven. So please don't use data-driven, because data-driven means the data you have. And the Murphy's law of data is that the data you have is not the data you need. So you need to be problem-driven. So data-driven, I think, is a wrong term. So then the questions here are, what data we need? How much? Is really big data? Really, it's not important if it's big data or not. If it's the right data, doesn't matter. But in most cases, it's not big data because it doesn't have velocity. This is the one that is harder. And if you have velocity, maybe you don't have variety. So variety is very important. So it's big data if you basically have many different types of data. Then you need to think about how we collect it, and then how we store and transfer it. Because if really big data, to transfer may be the main problem rather than storing it. If you need to move petabytes, it's not, you cannot do it easily through the internet. Now, the second set of questions is about understanding the data. So things that you need to understand from the data include the sparsity, how sparse is the data. Second, how much noise. I will get back to that. So basically, how much data is really not helping you. Redundancy. Redundancy is a type of noise, but it's a very important one. Basically, if you have duplicated data, because if you are using the volume of the data to weight anything, then you have weights that are not correct. There are weights that are will be a bias on the system. And then that's the next problem, biases. And the biases not come only from redundancy, but they come from social biases like gender, like race, like caste, and other things that may be important in India. So I will get back to this. And the next line is about the spam. So if there is a spam, I will explain what is a spam in the context of different examples, but you know spam in mail, but there is a spam in the web. And basically, there is a spam everywhere that you have an incentive to basically play around the system, for example, e-commerce, to have some economic gain. And then the last question, very important, any outliers. And the outliers are important because the outliers could be either interesting things, very interesting things that you need to check, or could be errors that are creating a problem, and this will be the worst case of noise. The next set of questions is analyzing the data. So here you come to the problems of privacy. Do we need to anonymize the data in any way? Even if we don't have names, if we don't have addresses, remember that there are many features, demographic features that are correlated, and you may need to anonymize them. For example, you don't want maybe to basically expose some information that can be inferred from the data that is private. Then we need to understand scalability. So are our algorithms scaling well? And I will talk about that. And then if we can visualize the results, because if we have really big data, the only way to understand the data is to have visual metaphors that allow us to understand how is the data. And finally, we need to remember this: the quality of any algorithm is bounded by the quality of the data that uses. In other words, as many people say, garbage in, garbage out. So if you don't check the data, then you already have a problem. You need to look at data. Many people never look at data. The only way to understand data is to look at it, and then you see if the data is good or not. There are many checks you can do very easily, automated, to find the quality of data. For example, you can count repeated values. You can check the minimum and maximum range of numerical data. Even for alphabetical data, you can all do that. Length of the fields and so on. Many, many ways to do quick check-ins to see if the data is reasonable. Now, what are the challenges? Here I will use a joke from Calvin and Hobbes, and this is something I do. Basically, if you read the joke, Calvin prefers to basically mess with data, so he's less predictable. I do this sometimes. I do things that I don't want to do just to make my personal data more unpredictable. And one thing here is that we know the few successes, but not the failures, and there are plenty of them. So if you want to know, for example, the current problems of AI, I suggest you look at this database, incidents-database.ai. And this has a lot of problems of what happens in practice. By the way, maybe I made a mistake in the, I make a small mistake in the website, so I will fix that. It's without the S, so it's an incident database. Okay, let's start with the first challenge, scalability. And here I will make you think about something that maybe you haven't thought about. So how to scale? So in the best case, if you double the data, you will double the time, because you need to read the data. So any algorithm will have to be at least linear time, so you read the data. So this is the best thing, you will double the time. However, in most cases, the algorithm is not linear, and then the time is much worse. But now, if we're measuring quality, for example, if you take any benchmark of any AI task, basically you have a quality measure. For example, you can take accuracy. Let's say you have two algorithms, one that has 90% accuracy, and another one that has, with the same data, 85% accuracy. And you will say, okay, the 90% accuracy is much better. But then you are not doing a fair evaluation. And I will explain why you are not doing a fair evaluation. Because what is important is not the size of the data. What is important is the time that you spend, for example, training the problem. So this graph shows the problem. So let's say you have a quality measure Q here in the y-axis, and then you have the size of the data in the horizontal axis. Now, and then here you have A1 and A2. And then here the 90% were here, the quality, so A1 is better than A2, you are working in this part. So you are working here. Is that fair? Well, that's not fair, because what you need to do is not to compare same size of data, but the same amount of time. And because A1, for example, in this example, is lower than A2, let's say with the same time, A1 really only processes this amount of data. So for example, only can get to this value. And then what is important here, if that's the case, you see that for the same amount of time, then A2 is a bit better than A1. So what this means, that in many cases, I can improve the results by just using more data because I have a faster algorithm. So there's a trade-off between time and volume. And in many cases, that's much better than trying to do to scale the A1, because A1, for example, could be a quadratic algorithm, would be very hard to scale. So this is a new line of algorithms that there's very little research that basically says, I will do it better because I can process more data than you. And the only way to do that is because I will be simpler than you, but faster than you. And one example is entity detection, for example, linear time and good quality, that will beat any system that does entity detection with a more sophisticated scheme that, for example, is quadratic or n log n, but it's not linear. There are other scalability issues, like, for example, downsampling and quality. For example, when you need to balance data because you have a very unbalanced problem, like in classification. There is all the problem of how you parallelize in distributed settings these algorithms. For example, MapReduce does not always work. MapReduce will be Hadoop. Does not always work for some problems, because there are problems that are much harder to parallelize. For example, graph algorithms are much harder to parallelize. The parallelism depends on the problem. It's not the same in all problems. And of course, for example, when you have streams of data, you need a different approach. Online processing is different. For example, when you need to learn from very dynamic streams of data, instead of deep learning, you need to use reinforcement learning, maybe coupled with some deep learning pre-trained objects. But in general, deep learning alone will not solve your problem because things are changing that much that models that don't last for long. And then you have the deep learning, and of course here is learning how to represent the data. You can transfer one representation to another. You have all the words of transformers today and language models and the idea of attention, where you focus in some part of the data to learn. And you need to exploit the context, which usually is not in the data. And this is something that is a limitation, and I will get back to this later. And if you really want to do it well, you need to add semantics. And here I will recommend an article that Gary Marcus published very recently that is titled "Deep Learning is Hitting a Wall." So I recommend that you read it, because sometimes people believe that deep learning can do everything, and the truth is that it cannot. Okay, the second challenge, noise and spam. Noise may come from many places. For example, may come from the measurements. Imagine that you have a sensor, that you deploy the same sensor in many places, and suddenly the sensor software has a bug. You will have hundreds of sensors that do the same mistake. How we will recognize that these sensors are wrong? Very hard, because they're all saying the same, because they have the same bug. So these kind of problems where, for example, the problem is not an outlier, but the problem is that all of them have the same problem, is something that we will need to lead in the near future. Moreover, when you have more than 20 billion sensors in the world, so now there are more sensors than people in the world connected to internet. And this has to do also with how we interpret the data. So spam is everywhere. Any place that you have an economic incentive to deceive someone, you will have a spam. And before, one way to fight this was using the wisdom of the crowds, like a democracy. The majority should be right, but it's not always true. In the example of sensors I said, if all the sensors are wrong, you cannot use the wisdom of the crowds. And another problem is really the wisdom of all of us if we're trying to use people. The truth is, the answer is no. Clearly, we have the wisdom of a few, because this is a power law. So the way people interact is that 90% of the people never is active. And this is called the Nielsen rule of participation, that he defined it in 2006. Basically, most people don't interact, they are just watching, and then means that there is no wisdom of the crowds, it's the wisdom of the people that really want to interact with the rest of the world. And they don't need to have to be right, so we need to be careful. The third challenge, and is the one that is maybe the most complicated right now, is redundancy and bias. So for example, are there any dependencies in the data? For example, correlations between values. Of course, correlation is not enough. We need to see if there's a causality. So if there is a correlation, and then it's also the causality, then we have some redundancy. So this is like a redundancy that's much harder to find, because it's not basically duplication, but it's the same. For example, let's say a typical dependency that will be correlated. You may have the same content in 10 different languages, and then you think that the content is important because you have 10 times that. But then you realize that every page is a translation of the same content. So really, you have only one copy, but you are counting 10 because it looks different. They are different languages. The next problem is duplication. So duplication is now the same content, so it's much easier to find because it's exactly the same content, although it's very important to check for near duplication. Like, for example, you can have the same web page and only changes the date, or only changes some signature that the website put to recognize that it's theirs, but it's the same content. So many years ago, when people were able to basically take the whole web and compute these things, they found that the duplication of the web was around 25%. We're talking about more than 10 years ago. At that time, also, we worked on this at Yahoo Labs and found that semantic duplication was even larger. So basically, that if you take paragraphs and take pieces of pages, then this was about 35%. So today, most probably, we are reaching like 50%. So there's a lot of repetition in the web. And the next problem, and one is harder, is biases. And here I have a paper that's one of my most downloaded papers. It's called Bias on the Web in Communications with ACM in June 2018, that I explain the vicious cycle of bias. So I have data bias, activity, or also can be called, I will put here, engagement bias. You have algorithmic bias, and we'll explain what is the difference between algorithmic bias and other biases. So algorithmic bias is only coming from the algorithm, not from the data. So for example, there are some cases where bias is amplified. In that case, we cannot blame the algorithm. Sorry, we cannot blame the data. We need to blame the algorithm. And finally, a particular case of algorithmic bias is the interaction bias. So it's the feedback loop between the user and the system. Let me give you an example of racial bias in data. This doesn't come from the US. The typical case is the US, but here I decided to use data from the England and Wales, so part of Great Britain. I think that will be more closer to your heritage. And here is the population of these two parts of the United Kingdom. Basically, most of the population is white, and it's in red, I don't know why, 85%. And then you have black, then you have Asian, you have mixed, and then you have Chinese and other. So the first thing that you can notice here is that you have a bias in the classification because China is also in Asia. So in this graph, the categories are wrong because basically you have Asia in two parts, and there is a semantic issue there. But let's put that aside. And then you can see how many people is arrested, how many people is prosecuted, how many people is convicted, and how many people go to prison. So for example, if you see the black population, it's about, I would say, less than 5% that is in the population, but it's 3 times more arrested and 4 times more in the prison. So there's a clear race bias against black people. So this is from the government. So this graph is from the Ministry of Justice of 2014. So this is real data. And then if you use this data, you will learn to be biased against black because it's already in the data. And there's a paper, very interesting paper by Kleinberg et al., which is called Human Decisions and Machine Predictions. I thought I had the reference here, but basically, and the problem is I don't have animation now. It's an example of using machine learning in the justice to see how well they can predict the same problem on courts, and it's a problem of bails in the state of New York. And in the state of New York, 18% are black, 13% are Hispanic heritage, like say Latin American, and then 32% in total. Now, as in the case of the data from the UK, you get also people coming to court. You also is already biased. So for example, 49% is black, 33% Hispanic, and 82% from these two minorities. So here you have a clear bias in the rest of cases, like in the UK, but this is in New York. And then the judges increase this bias, so they increment the population that goes to prison from 48% that come, from 49% to 57%. However, they decrease the bias in Hispanics from 33% to 32%, so I guess that's more white Latin Americans, and that affects this ratio. But still, if you sum the two minorities, you jump from 82% to 89%. Now, what is the problem? Is that the algorithm learned to be biased. and here I will discover the rest of the table, you will see that the algorithm learned to increase the bias in Black people to almost 60% from 57%. Also learned to decrease the trend of Hispanic, so lower the 32% to 30%, but in total increase the minority group to 90%. So now 32% to 90%, we went to like the 2.5 bias to almost 3 bias. Now, we can play with the model. So the model was able to decrease the crime rate to 25%. So that was good. But if we use, we tailor the model to say, to be less racist and to basically learn about the less racist judge, then still the model is able to improve the system by 23%. So the model is biased. It amplified the bias, so we need to blame the model. So this will be an example of algorithmic bias. And then we have a dilemma. And the dilemma is that what is better, a biased algorithm or a noisy judge? Because this happens because of noise, so because of spam, what I was mentioning before. Human decisions have a lot of variance. They're not the same. So you can think that this is what we want, A, exact. For example, we're targeting we are really in the center of the target. B is noisy. So this will be a judge that is not racist, a lot of variance in the decisions. So basically more like irrationality. Then this will be the algorithm. The algorithm is biased, so it's not matching the center of the target, but it's going systematically to the right and to the bottom. And this will be biased and noisy. So you have a deviation that is systematic, but also you have a variability that spreads the target. Now, the truth is that we are here. So algorithms are biased, but they are not noisy. Why? Because for the same data, for the same kind of case, you get the same result. This assuming that the model is correct and assuming that the data captures the whole problem. And I will get back to this. So in justice, it's very hard to capture with data all the context of the decision that you are making. Another problem that's very important is that when you are using a machine learning model to do justice, you are not doing individual justice. So justice is about this person that is being judged. It's an individual decision. However, if you're using a machine learning model, you're averaging the decision among all the people that have similar cases. So basically, you are normalizing the decisions. And that's why you don't have noise in the case of the algorithm. So in some sense, it's just because you take the same decision for similar cases, but you are losing the individual decision because the context is not captured by data. And this is the problem. So that's why it really is non-ethical to use these kind of tools for justice. So things that are human shouldn't be mixed with machine learning. Things like trust, justice, and also, for example, ethics. Now, last year, Daniel Kahneman, with other co-authors, and you know Daniel Kahneman is a Nobel Prize in Economy, published a book called Noise, I recommend it, basically about how people don't take decisions consistently, and that basically creates a lot of noise in the data, and not only bias. So really, judges are here. They're biased and noisy, while algorithms are here. They're only biased. Please remember this because this is a very important part of today. Let me give you some other examples of data bias. So for example, sorry, I don't want to give away the answer, so because I don't have animation. So this is an example from one of my PhD students. These are biographies of women in Wikipedia. So you see that if you take the year of birth of the person, you see that the minimal is near the French Revolution. Maybe that's not a coincidence. And then there are more and more women that have gained fame, and then they appear in Wikipedia. We are close now to 25%. Still, there's a lot of systemic bias, but here there's another bias that is much bigger than the systemic bias. And the bias here is that basically, if you take, for example, people, only 11% of the women, of the editors of Wikipedia are women. So there are very few women writing in Wikipedia. Now, there are more women because this is partial information. Why? Because it's not compulsory to say your gender in Wikipedia, so many women prefer not to say it, to not be harassed by the other men that is in Wikipedia. But also there's another question. Do women have the same opportunity to become editors of Wikipedia? And probably in India, the answer is no. And this is something important you need to remember, the context of what you are asking. And if you're interested in this paper, this Eduardo was my PhD student, and it's the paper is called First Women, Second Sex, and it's the gender bias in Wikipedia. Let me give you an example of engagement bias. I was saying before, is the wisdom of a crowd? The truth is that it's not. So with another of my PhD student, Diego, we tried to answer the following question. How many users produce most of the content? So basically, which percentage of users produce half of the content? This was the question. We used a small Facebook data set that was available for the Katrina hurricane in New Orleans, and there we found that 7% of the people did half of the post. So that means that the other 93% of the people did the other half of the post. So this is what it means. So how many people do the first half, and the rest do that second half? We also look at Amazon reviews in movies. So this is a collection that you can download from Stanford. And we found that 4% of the people did half of the reviews. When I saw the result, I told my PhD student, this cannot be right. I mean, we cannot have 4% of the people doing all the reviews. So a big part of the reviews. And we checked, and what's the case, and then they said, okay, then this must be a different process. It's not about reviewing because you want. And then 1 month after we published this work, Amazon started to sue. So there's no, I don't know if it's causality, I don't know if it's because of our work, but it was exactly 1 month, so there's a correlation. Amazon started to sue fake reviewers. So basically, people that were writing false reviews for money, and be careful, if you don't have too many reviews, they may be false if they are all 5 stars. And this is something that is going on until today. So you can look every year, and basically Amazon keeps this crusade against fake reviews, but because there are many, so this is the spam in e-commerce, fake reviews. Now, we look at this because we found that it was very interesting that very few people did half of the reviews. So we wanted to check the quality of the reviews. So basically, adding content means adding wisdom. And we use the stars, and we use something called text entropy as a proxy of quality, and we saw that there was a correlation between the average number of stars and the text entropy, so that was a good proxy. And then if we sort the reviews by quality, this 4% became 2.5%. Basically, 2.5% of the people did the best quality reviews. And this is another indication that maybe they're getting paid, because if you want to do a quality review, you need to take more time. Well, let's go to the other examples. Influencers, 9% of the people that basically interact with them, they put like, they put comments and so on. And then there are 90% of people that just watch. So these are the lurkers. They just watch. Now, that was in 2006. I think today is worse. So this 1% is less than 1%. So it's much smaller. And the people watching is maybe more than 90%. So this is the case of Twitter. So in Twitter, we found that 2% of the people in a very large collection about 10 years ago, and 2% of the people did half of the tweets. This is not surprising. They are not getting paid, but this is I guess, the effect of ego in the web. A lot of people want to say things, and this is 2%. And finally, the last example is from Wikipedia. You may not know that 2,000 people wrote the first 50% of entries of the English Wikipedia. And this may be, of course, they were paid by the Wikimedia Foundation. And this may be the difference of having a Wikipedia today or not, because if you want to contribute to something, you will never contribute with something that is completely empty. You need to see it at least half full, and this is a percentage. Very small number of editors did the first half. Now, with this student I already mentioned, Diego, we also analyzed another problem that I was interested in, what I call the digital desert, is how much content in the web is never seen. And we found an upper bound and a lower bound. The upper bound is that we check data that is available in Wikipedia. So all the usage of Wikipedia is public. So we check that all the changes and additions of 1 month were never visited in the next month. So basically everything that happened in May 2014 were not visited in June 2014. And this was 31%. So of course this number depends on the length of time, but it's interesting that something that happened in a month, basically 1/3 of it was not checked the next month. And the lower bound was that a bit more than 1% of the Twitter content was done by people that didn't have any followers. So basically, if you don't have followers, it's impossible that anyone will see your tweets. Even if you search for it, you will not see it because it will be at the end of the ranking because you don't have followers. So this is like going to the desert and screaming. Yeah, maybe cathartic, but no one is listening to you. Next example. Another example of algorithmic bias. Let's say that you have a picture, like this picture from London, and you upload it, let's say, in Flickr, write 2 tags. Here the tags are London Eye and Thames. And then you are a computer scientist, you say, okay, I will help people and do a correlative filtering approach to recommend tags. So basically, I will recommend tags that are in the same context of other pictures to improve this. So you get, for example, London, England, UK, River, South Bank, and so on, and the people will click in the ones that look good, and then I will increase the tags of the picture. So what is the problem? You shouldn't do this. That's why I have this cross here. You shouldn't help people. Why? Because then the next time people will put only 1 tag. Because the people are so stupid, they learn, okay, if the system is recommending me the tags, why I will put many? I will put only 1. But then if the people realize that this is using deep learning and can recommend tags even without you putting anything, people will not put any tags. And why that is bad? Well, that is bad because the only way to learn is to get data from people. And if you incentive people to put less data, it's like killing yourself very slowly. So if you have a folksonomy, so a folksonomy basically is something based on data coming from people, don't help people. You can use this idea of tags to search, but not to basically recommendation. Let me talk about interaction biases. These are maybe the worst biases that you may have. And here I will explain you the cases. So the first, let's say this you will recognize from where this page comes. So this is an e-commerce, and then you have many biases in the interaction. So the first one is exposure or presentation bias. So basically, here you are seeing maybe 1, 2, 3, 4, 5, 6 products, or 5 products and some categories. But how many tennis pros there are? Thousands. So this is like an iceberg. But it's worse than the iceberg because you are not looking at, let's say, the 1/7 on top of the iceberg. You are looking here. this is the ice cube on top of the iceberg. You are just looking at a very small percentage of the things that you could look at. So this is exposure bias. And this is very well used in health, but now it also applies to basically e-commerce. What other biases you have here? Position bias. So basically, in the Western world, we read from left to right and from top to bottom. So you will always look first here. This is a cognitive bias that you haven't coded. Maybe in other countries it's different. I don't know if in India you have also, you need to read in different directions, but basically you will be tailored to this kind of reading. And then another position bias, a particular one, is ranking bias. So this, let me put this, just to make sure this is an example of position bias, is that people will click more on this product because it's in the first place. So people believe that the ranking is magical and it always works. And people will click less on the second thing. And then this ranking bias, you can fix it. So there are ways to fix this. And you need to be aware of this because otherwise search engines will fool themselves thinking that the first one is best because more people click in the first one. Then you have social bias. And social bias has to do with what I was talking before about basically the stars. What will be social bias is that you will buy this product because this one has 5 stars, but not this one because this one has 4 stars. So basically, what other people think, including fake reviews, will change your judgment. And this is social bias. And then you have interaction bias. Interaction bias is everything that happens in the interaction and depends on every person. For example, some people need to move the mouse all the time. Some people need to click fast. Some people don't scroll and then they never see below the page and they don't know where to scroll. I don't know if you have, for example, you have a Mac. The only way to scroll is to put the mouse here to see the scroll bar. I wonder what happens if you never find that. You need to be an expert to find that. Let's imagine the first time you are using a Mac, you will waste some time until you find that functionality and so on. So these are interaction biases. And interaction biases is a cascade of biases. So it's not only one bias, it's a composition of bias. So for example, here you have all the biases that I mentioned, and here I have more interaction biases. And then everything to the left of this line is data and arithmetic bias, and everything to the right is what I call self-selection bias. These are cognitive biases of the person. So this is the cognitive bias of the user. So this will be, and then I can send the slides so you have it, cognitive bias of users. Okay, all of this, you can find it in this paper, Bias on the Web, Publication of CM, June 2018. So this is the full picture. So you have data bias, and another bias that you have is sampling bias. Basically, it's very important you get the right sample, not only in the types of objects that you sample, but also in the number of objects that you sample. One problem that we have, and I have a paper on that you can check on basically sampling bias, is that because we are dealing with power laws in the web, typically to find something needs much more data because it's very hard to find that. For example, probability of a click. Probability of a click is like 1 in 1,000 or even worse. So to find something that happens one in 1,000, you need a lot of data. But sometimes you use the standard sampling size, and that doesn't work because that is for a non-biased distribution. So for example, that's for a non-skew distribution. So for skew distributions, you need to use different formulas to estimate the size. You can look for a paper I have in doing the right sampling size. And this another bias I haven't talked here is the second order bias. Basically, what do you do with the data you gather from the interface? For example, one thing is personalization. So your data goes back to the algorithm, and I will talk about this. Or, for example, your data goes back to the web, and also I will talk about that, yes. So let's see the first case. The first case is the filter bubble problem, like the Truman Show. So Truman tried to get out of the bubble when he learned he was living in a bubble. If you remember the movie, you saw the movie. But many people don't want to get out of the bubble. So this idea is basically the Matthew effect. The rich get richer and the poor get poorer. And here we want to avoid this syndrome of the poor gets poorer. So this is called also the tunnel effect, not only the filter bubble. For example, I will never be able to, let me pick one person, one Jew, like I will never be able to recommend something to Rimi that she doesn't know, and if she knew it, she would like it, because it's not in her data. So this is not in her data, so I cannot recommend that to her. I can use, for example, corrective filtering to break that, and then I can recommend new things to her. But still, the whole system is in a bigger bubble because there's more data that I don't know. For example, it's something new. I don't know that group of people will like that. So this is the network effect of bias. And there are some solutions like diversity, novelty, serendipity. And one that I would like, but I cannot find, is what I call my opposite side, my dark side. For example, I want to have the recommendation most weird to me, the one that I really will not like, so the other extreme. And not because I will buy that, it's because I want to know basically how far I'm from other people. Because I think today we believe that they are closer to each other than we are, but that's not the case because we have wars and we have other things that happen in the world that shouldn't happen. So the second one is second order bias, and this is a problem that we analyzed with another of my PhD students, and this is the one that I was talking before about semantic redundancy. Okay. So let's say the following. So let's say you are writing a blog, and here will be an example of a ranking bias. So let's say you're writing a blog, and you search for something in a search engine, and then you get these 3 blue pages. So basically, you get 3 pages, and you can take 3 red pieces that are paragraphs to write your new blog, and you put these 3 red pieces here. This is the new blog of you. Of course, you are not doing plagiarism, so you will put this in quotes. You will put the author, the name of the author here, and also you will put a link back to the source, basically because you are just reference citing them. You are doing research. You are not doing plagiarism. But now you have only stuff written by other people, so here you feel a bit of shame, and you write something. So this green part, you wrote it. So now at least the blog has some content from you. And then you feel some ego, and you put your name on the top. So this is a typical mashup. It's called a mashup that is made from comments from other people, plus your comments, and then your name because you are the author. Well, what happens with this? This is second order bias because when you put this back to the web, then you are reinforcing the belief of this search engine that these 3 pieces belong to good pages. So basically, you reinforce the belief of this that these 3 pages are good. And this is more than ranking bias, because this is not about clicks here. It's about having more content like this, and then you're reinforcing the ranking that these are good. So you are reinforcing not the position, you are reinforcing the ranking function itself. And this is much more dangerous. And what happens then, the redundancy grows. And when we were able to study this, we used the genealogical trees of the web. So basically, we were able to find the ancestors of every page and check if the content was repeated or not. We found that redundancy was much, much larger. Now, the next problem, sparsity. The long tail of data. So I will show a different kind of long tail. So let's say this is a size of data. So this is, let's say, data size. And these are companies. Well, very few companies have big data. Only internet companies and basically only companies that are using internet have big data. If your business is not really in the internet, you don't have big data because you don't have velocity. And this is something many people don't understand. Most companies in the world have a small data. For example, health is all about small data. It's all small and medium-sized companies is a small data. So 99% of the problems of the world are small data. And I don't know why we are talking about big data. We should be talking about small data because small data, for example, is 99.9% of all the problems in India. So please look at small data. And why? Well, there's a book that was published in 2008 by Martin Lindstrom called Small Data. And here is a summary of the book, but also of other things that are important. So basically, small data is the right data for your problem. You don't need big data. Usually, small data is more precise and complete. Small data is about us. Most data that people consume is small data. Your data is small data. So everything in your mobile is small data. Small data describes every person in a given context. Small data can be understood and interpreted by humans. And very important, and Martin chose with many examples, most innovations are triggered by small data. You gain your insights on samples of data that you analyze. So I wrote a survey for NSA. In 2018, you can find in KD Nuggets. Sorry, this was got the gold award for that week in October 2018. But finally, recently, someone really famous like Andrew Ng did the same. He said, "I'm vegan AI," and this is something we should do. So he has this article in his interview in IEEE Spectrum this month, and that basically says that you need to unvegan AI. So this is important. Sorry, yes, I want to I was checking the reference, so just to make sure that you find it. This was February, not March, it was last month. Okay, so please, small data, another important concept that you need to get from this talk. Because big data is easy, small data is not. Let me give you an example of another of my PhD students that she was trying to basically predict people with dyslexia. This is about 10% of the population with machine learning. And this is unbalanced data. And here is an example. We got only 4,000 children in Spanish, even less in English, 1,500. But for example, we got much better accuracy with 1,500 in English than with 4,000 in Spanish. So here is a good example that sometimes the amount of data is not important, is again, the complexity of the problem. So a question for the end of the talk: why is easier this problem in English and it's more difficult in Spanish in spite of having more data? So you have almost 3 times more data, the accuracy is 9%, so basically it's 10% worse. So question for the end, if someone can answer the question, would be nice. Then you understand the complexity of the problem. Also, the cost of false negatives, very important, having dyslexia, is much higher than false positives. And this is true in all medicine, all medical problems. It's much better to tell a person that is ill, and then when goes to the doctor says, no, you don't have anything, you are okay, than saying to the person that you are not ill, and basically that person will die because was not diagnosed with a cancer, for example. And I have talked to doctors, and doctors even tell me that they are willing to see 10 more people, let's say 10 people that is not ill, to basically don't miss one that is ill. So in this case, using the best accuracy is the wrong point of operation for your model. You need to use what for example, the doctor wants, or for here, for what we think that is, or a specialist will think that's the right factor. For example, you can say, okay, I don't want to use the maximum accuracy like here. I want to use that false negatives are half, are half of false positives, or maybe even less. Before last challenge, privacy risk. And here you have problems of anonymity. So in 2001, Sweeney found that basically 80% of all people in the US could be identified from public data. Remember, in the US, you have, because of the Second Amendment, it's not valid to have a national ID card. So the proxy of a national ID card is your driver's license or a state ID card, but it's no federal ID. But you can predict almost all people using public data. And then this was the thing that triggered this concept of K-anonymity, that basically you hide people with a K plus one other people that have the same data of you. So this is also related to a statistical database. And now we have the GDPR, and I guess you are familiar with that. But even if you have anonymity, in other contexts, it's very hard to basically hide your name. So this is a real case that happened in 2006 when American Online released a set of query logs. This was anonymous. Every person was mapped to a random integer. And then some journalists started to gossip on this data and found that they could basically predict the name of a person. That was the person, this number, for 4 billion and something, because of the queries she asked. So she asked things like landscapers in Linear, Georgia, so you know where the person is. And then she asked things about drugs, and basically crossing the data, all these queries, they were able to realize that these queries came from this woman, Thelma Arnold, that at that time was 62 years old, that was living in this place in Georgia. And basically they went to her house. They asked her, "Are these your queries?" And she amazingly said, "Yes, these are my queries." And then they asked her, do you mind being mentioned in the newspaper? And she said, "No, it's okay. I had never been in the newspaper. It would be nice to have a picture of me in the newspaper." And she was in the first page of New York Times. This is a huge public relations scandal. Why? Because basically this is illegal. You shouldn't give data away that allows you to de-identify people. So this shows that the problem was much harder than we thought. And this was not the first case. Later, I don't know if you remember the Netflix challenge that was 10 years ago, or 12 years ago, was basically to find a better movie recommendation system for people. And they were sharing, again, anonymous choices of movies. But then some people from a university in Texas, using data from this very famous site of movies that basically you can rate movies, were able to, again, identify a person. And that person, from the choices that were in the data, in the private data, you could infer that was basically homosexual. But she never publicly said that, and then she sued Netflix, and at the end they decided to end the contest, end the challenge, and also basically pay this person some amount of money that was private because of basically exposing her sexual preference. So after that, it's much harder to get data shared by companies because it's clearly much more easy to identify a person than before. So we did some research at Yahoo Labs to see how difficult it was to identify a person. So we look at using your queries to predict gender, 84%. using your queries to predict age, 79%. And even the location, using your queries to, for example, predict the first 3 digits of your zip code, 35%. What's even worse, there are many people that ask their name in the web. So if someone has never asked his name or her name in the web, please put it in the chat, say me. I found only one person that never has asked her or his name in the web, and I was hard to believe that person. So something that we all do, that is vanity. And then if you do that, well, with 9%, I can predict your surname or your name. And with 1.2%, this is the amount of queries that are vanity queries, I can predict your full name. So next time that you feel the urge to look for your name in the web, ask a friend to search for your name, and you can search for her or his name instead, and at least you will basically mix the data. So even more, in 2019, there was a very interesting set of articles from New York Times, where it's called the Privacy Project, where they use apps data, mainly games. So basically, there are apps that sell data about games. And what I have here in the map is what Trump did in, I think this was in 2019, what Trump did when was visited by the Prime Minister of Japan. And how they can know that this was this? Because one of his bodyguards was playing a game. So basically, with this data, you can find amazing things. For example, another thing that they found was like the exact house and work of a person, because it was the only person that was playing the same game in New York, going by train every day was a teacher from every weekday from her home to a school. So from app data, it's even easier to basically find this. So the last set of challenges, legal and ethical issues. Ethics is very hard because ethics is cultural. So for example, the Buddhist ethics is very different from a Christian ethics or from Muslim ethics. So this is the thing. Can we have international consensus in the legal terms? It's even hard, very hard, because, for example, we have human rights of the United Nations, but not all countries belong to the United Nations. So we still don't have international consensus. We still have wars. I don't know if you know how many active wars there are. Today, there are 24 active wars in the world. And we talk only about the few because we have biases. For example, maybe in India, you know much better the war in Myanmar, the civil war. But in other countries, they don't talk about Myanmar. So let me give you a real moral dilemma. I don't like the trolley dilemma. If you know about the famous trolley problem for ethics, because it's fictitious. But let's give you one that is much more real. I know that self-driving cars will kill less people. You know that in 2018, an Uber car killed a woman in Arizona, and then other people have died because of the automatic pilot of Tesla and so on. So there are around between 10 and 20 people that have been killed because of playing with automated functionality. Well, but still, I'm sure that, for example, in India, a lot of people will not die. So let's say that dies 10% of the people that died before. That will be a huge improvement. What is the problem? That this 10% is not a subset of the 100% that dies today. This 10% will be, let's say, 8% of people that before will die anyway, and 2% that who have never died, but now dies because of self-driving cars. This will be like the woman in Arizona. This will be a small kit where the system doesn't recognize that it's a kit because it's too small and was playing like hidden, or was like a ball, but not standing. So basically, many of will be old people. So basically, more vulnerable people will die than before. So the question, and most of the people that will save, sadly, will be men driving fast in their cars that now will not be able to drive. So this is an ethical dilemma. It's okay to save, for example, a lot of aggressive drivers and careless drivers, and then because of that, killing, for example, some women and children and old people. This is an ethical dilemma where we cannot decide. Society has to decide. So ethical algorithms, no. Ethics is a human trait. So you cannot talk about ethical algorithms. You shouldn't talk about trustworthy AI. You shouldn't talk about ethical AI. You shouldn't talk about just AI. Justice, trust, ethics are human things. When you put those things in humans, you are just doing anthropomorphic bias. You are trying to say that these things are humans. They are not. They are just robots. They are a creation of us, and they cannot be much better than us because we are the masters. If we believe that we can create the singularity or super intelligence, then we are playing God. We think that we can build something better than us. This is very arrogant. So and sadly, there are many famous people that has this arrogance that think that they can create something better than us. They are playing God, and most of them are men, sadly. Okay, in 2017, the ACM US policy, technology policy committee, which are one of the members, created these 7 rules for algorithm transparency and accountability. So I will not read them. You can read them. This is what they think we should have. Now, we don't need to be perfect. We just need to be better than humans in some dimensions. But one thing that appeared in a recent book, that's called Judging Machines from Cesar Hidalgo, is that we are harsher on machines than on humans. So for example, to err is human, but this is not true for machines. So in that case, we don't try to humanize them. We expect them to be better than us, but the question is why? Learning from us doesn't make us perfect. For example, that's why they get our biases, they get everything that we have because they're using our data. They're replicating us. So some bad human practice, and this is based in a nice paper by Gina Matthews, that's also in the ACM US Technology Policy Committee. I will not read all of this, but for example, learning from the past will not change the future. So try not to learn from the past. If you want to use historical data, you need to do something to change the future. Otherwise, you are just replicating the past. Not checking for spurious correlations or protected information, very important. Reusing codes in a context that was not intended for that code. Many times people take things from GitHub and then apply it to a different problem. Be careful. For example, using human in the loop when we should be in control. Don't say human in the loop, much better to be in control. And the most important one, very important, the last one, don't use the data that you have or the data that you think is good. You need to look for the data that you really need, the right data, as was saying before. Sorry. So some recommendations for us. Design for people first. Have a deep respect to our limitations. I'm wondering if I skip one important slide about the limitations. This is weird. Sorry, here, yes. Hard learning problems. These are the limitations. First, to be intelligent, you need to filter data. You need to abstract data. For example, when you see an animal, you don't need to see 10 pictures from different directions to learn what is a cat. So I'm sure most of you will recognize which animal here is in the right. Most machines will fail to recognize what is this, right? Because this is a weird picture from a cat taken below forgot now the word, below a glass table. And this is if you want to read this is available on the web. There's a very nice story from Borges, a famous Argentinian writer, that is called Funes de Memorios. That was a person that couldn't forget anything. So it was impossible for that person to, it was like a machine. Everything that he will see, he will remember. And then if you meet him in the street and you will ask him, oh, how was your morning? You will need to wait 3 hours because he will tell you exactly what happens in these 3 hours. And if you're lucky, it will take 3 hours because sometimes telling every second takes more than a second, so it will be much longer. Second thing, very important, you cannot learn what is not in the data. Impossible. And particularly data that doesn't exist. For example, this is the main problem of self-driving cars. There are so many incidents that may happen in the future that have never happened in the past. So, impossible. And another thing related to this that is very, very important is you can apply it to justice. Data cannot capture the whole problem. So if you think that data captures the whole problem, you are fooling yourself. Data is a proxy for the problem. But for example, the context of, say, a court is impossible to capture. For example, exactly what is happening today in a case in court will not be captured by data. Third thing, I hope I convinced you, accuracy is not the key. The impact of errors are, because many of them may harm humans. So the example I like to put is that, let's say you go to a building and you go to the elevator and the elevator says works 99% of the time. This is what we are doing today with AI. We are saying the time that we have success. So imagine that you have an elevator says 99% of the time works. Would you go to the elevator? I would never go inside that elevator. However, imagine that the elevator says 1% of the time doesn't work. But when it doesn't work, the elevator stops 100% of the time. So I will go up to the elevator because I know that if there is a problem, the elevator will not kill me going down. This is what we need to do with AI. We need to say what is the harm, not when it works. For example, I prefer to use a Buddhist car. A Buddhist car will be one that doesn't drive fast, that respects all people, that will make sure that everyone is safe, and doesn't work so well. So 90% of the time you get on time to places. But I prefer to use that car that, for example, a fast car that 99% of the time gets on time to where you want to go, but kills more people. So there is a red line. Doesn't matter you work well 99%. I prefer to use the car that doesn't kill people. These are the red lines we need to put, and these are the things that we need to change in the future. And finally, this has to do with the arrogancy that I mentioned. How many systems, for example, let's say you do a classifier, and you get confidence 0.3 that what you are seeing is a cat. You shouldn't say it's a cat. You should say, I don't know, because you are not confident that it's a cat. But today, AI is arrogant, and people is just saying, okay, this is the answer. And this is sometimes they put the confidence, sometimes they don't put it. But if really you have low confidence, the smart answer is saying, I don't know. Smart people, when they don't know, they say, I don't know. Don't smart people try to lie or invent story when they don't know. So this is important. And the recommendations, so here I have the recommendation, design for people first, remember the limitations, don't reproduce the past, have an ethics board if you want to do something new, improve explainability. What I said before, I want to have humans in control and machines in the loop. We are the masters. If we want to play God, let's play it well. don't play it like we don't know what we're doing. Human in the loop is just to have someone accountable. In the example of Arizona, of the person that was killed, Uber very fast got an agreement with the family of the woman, and then the state of Arizona had to do something because a person died. So the state sued the driver that was in case of a problem, because she was looking, sadly was a woman, a poor Hispanic woman being paid a minimal wage, and she was bored, so she was looking a video when that happened, was at night, and then she couldn't react on time to avoid the car killing the woman. So at the end, a vulnerable person was being accountable of something that probably is more Uber's fault than this woman's fault. Okay, so we are finishing, so we to have some time for questions. So I'm not worried about artificial intelligence, like the joke on the left. I'm really worried about real intelligence, because even people with PhDs is doing all these ethical mistakes and all these evaluation mistakes that we're doing today that we should change. So prove you are not a human, as the computer, and the robot says there are no more humans. The computer says correct, and they both laugh. But they don't laugh because they killed humans. They laugh because I guess humans will kill themselves if we don't continue in the right direction. And here I would like to quote Harari, that says the real problem with robots is not their AI intelligence, but the natural stupidity and cruelty of their human masters. So the problem is us, not AI, not robots. If we do things well, the world will be much better. So there are many things that may change in the future. So for example, do we want privacy in health? It's very hard. COVID has shown that that's a fallacy. We can have privacy and also have good health. Software insurance, if we don't do things right, insurance companies will do it for us. And this will be really bad, because then developing software will be much more expensive. And I think we don't want that as a profession. Augmented humanity. So now we have things like plastic surgery. Let's say in the future we have augmentation of humans. So some people will put cyber parts in them. This will create more and more inequality in humans, because rich people will be able to use these parts, but poor people will not. We don't want that future. We should try to decrease the inequality gap, not increase it. So technological change in overall is good, but we have cases where, for example, we have been manipulated by social media. Here I have some cases like Philippines, China, but we have Brazil, we have the US, we have, I guess I can have a list of countries here that have been manipulated. Even India has some problem of manipulation of fake news now. So I like to read science fiction. So if you read The Naked Sun by Asimov, Solaria was a world where people lived alone, and the closest person was like 1,000 kilometers away. Everything was through internet. Do we want that? We are going in that direction. With the metaverse, it's even worse. We are going that way. Really, we want to change social interaction for something that we are looking in a virtual reality glasses, or we are looking at our devices? I don't think so. And if you saw the movie Arrival, maybe the solution is that some aliens come and force us to talk. Because today we have the 3 powers that are not talking, and we should. So I think now I can take questions. So this is my book on information retrieval. That there is a special Indian edition that is much cheaper if you want to learn about information retrieval. But most important, remember, you need the right data. The right data is maybe small data, doesn't matter, but needs to be quality data, and there you start. So the 3 questions: is your application ethical? Do you have a science facts that back up your application. For example, there are people like trying to predict sexual orientation or political orientation using your face. That's pseudoscience. That's garbage. And then having the right data. These are the three main things, three main questions that you need to do, basically to ask when you start using AI. So I don't know if you have questions. We still have like 20 minutes for questions.
If any one of you have questions, kindly paste it in the chat box, put it in the chat box. Sir will answer those.
There's no questions, really.
For the participants who are online, is somebody looking at the questions?
Yes, sir. We are just putting them.
See, I think one of you can directly ask rather than putting in the chat. You can just ask those questions.
Yeah, read the questions, please.
Sir, till they are doing it, I have one question, if you please permit. Sir, you made a very important point when you gave the example of that elevator, that just saying that the system is going to work 90% of time and nobody would be happy, but that 100% of time it will not go down. We are more interested in that. So my question is, sir, like today AI or whatever systems we talk about, can they ever tell anything which is 100%? Is it possible, like today, to build a system using whichever AI technical algorithm, which we can say whatever we wish to say, can it say anything 100%?
That's a very good question. I know some examples that achieve 100%, but the problem that is with the data they have. So basically, that's 100% on the data they know, but you cannot say that it's 100% in the data you have never seen. So even when you get 100%, you cannot be sure that it's 100%, because basically you are evaluating with a subset of all possible data related to that problem. So this is a very good point. Basically, even if you get 100%, you are not sure.
Yeah.
So this is like, for example, it's a very good example. There's a book about that. It's called The Black Swan. I don't know if you read that book. For example, in Europe, they believed that all swans were white. And this was the case because all the swans that they see were white, right? Mm. But then when they reached Australia, they found that there were black swans. And then it was something rare because they had never seen it. But now we know that they are black swans, so we know that. But for example, even the person that wrote the Black Swan book didn't know that in the Patagonia, there are swans that have white body and black neck. So there are swans of both colors, but most people don't know that. So this is something like, there are many things that are obvious to us, but only after we know them, but not before we know them. And this is the problem with knowledge. So, for example, anyone here, anyone in the 48 people here, knows what we can say if we see a cat of 3 colors. Anyone knows what we can say if we see a cat of 3 colors? Anyone knows a bit more biology than the standard? You can put it in the chat if you want to. Okay, there's something in the chat, so let me check what is in the chat. Okay, so I will answer that query later, Anne-Marie, but anyone knows about the 3 colors? No? Okay. Next time that you see a card of 3 colors, then you can do a bet and maybe earn some money. You see a card of 3 colors, you ask a friend, I can guess the gender of that cat. And if the person says male, then you bet, because a cat of 3 colors can only be female. This is genetics. So now it's obvious for you because you know it. Before it was not obvious. And there's a book about that. Everything that is obvious is only obvious because you know it. So don't let common sense fool you, because common sense is the less common of all the senses. Now, the question of Anne-Marie is, which skills are needed to be expert in big data? So I would prefer to change the question is what skills are needed to be expert on data science, because I will say that most of the problems you will find in your life are not about big data, it's about small data. So you need to be very good at data science. So I would say you need to have a good mathematics background. So you need to know about linear algebra, statistics, probabilities, and so on. You should be a good coder, so you should understand about algorithms, so you understand mathematical logic and so on. So basically about object-oriented programming, a lot of things that have to do with being a good programmer. And then I think you need to practice these skills that are more soft, but are related to think well about the problem you are modeling. So for things that are like if I want to decide something, we should talk to the users. I should talk to the people that know about the problem. Today, one of the problems we have in computer science is we are taking decisions that are not of our competence, so that we're not expert on. For example, we are saying, oh, I will do this medical application, but we don't talk to the doctors, or we don't talk to the patients. That's the problem. So, and when I'm saying I'm thinking, it's like thinking at the right level. So, okay, what I need to understand the problem to have the competence to do this. And this includes, for example, visual skills, includes data mining skills, data understanding skills, a lot of humility, to understand that you don't know everything, and so on. So these are the soft skills. I think a good data scientist is the one that really puts everything in context and learns from other people to do the best possible solution.
So we have another question. How
Yes?
do we know if data is right or wrong?
Yes, good question. So I have mentioned that. So first we need to do some checks in the data. So first take a sample, take a small sample, and you check it. You check if all the samples you have is reasonable. So basically you believe the data. So it's, for example, is in the right range of values, if numerical. If it's text, makes semantic sense. If it's other things, you check that looks valid. So basically, you need to take a sample, let's say 100 items, even more, 1,000 items. You can use crowdsourcing and check if the quality is good. Now, what will happen is that you will find problems. And then when you find problems, you need to think. When you find problems, it's like data mining. You have the answer. You have the answer, and then you need to ask the question, why I have this answer? And this may be a question. For example, could be a faulty measurement. Could be some assumption that you did that was wrong. So you will find the answer, and then you will come up with a question that will solve the problem. So this is the second step, and this has to do with data cleaning, data imputation, for example, missing data, has to do with data, the data variance too. So basically, you check all these things that you're sure, okay, yeah, this makes sense. If I have missing values, I can impute them. If I have missing values, I can make sure I don't take them in account. So putting like a null value, and then null values are not taken in account. If I have an error, changing that or converting that to a null value. So it's better to have a null value than having like an error in your data, so and so on. But all that takes time. So a good AI application will take 90% of the time preparing the data. And this is boring, I know. but we can automate it. So we can do tools to automate the quality. For example, you can check things like, very simple, find the maximum and the minimum on numerical values and see, okay, what is the range? Does the range make sense? Is that possible? Change what is the most repeated value. For example, you find the value that is repeated 100 times. Is that possible? Is that okay? The problem is that depends on the problem. So I cannot give you a rule saying you need to find this. But there are many, very common sense things, although I already said that common sense is not always obvious, to do this and to find if the data is good. But first, you need to look at it. A person has to look at it. And if you don't know about the problem, you need to ask an expert to look at it. So for example, if it's medical data, you cannot look at it. You need to do a sample. The sample has to be very good, so to cover the whole spectrum of the problem. And you need to ask a doctor, can you check this small data sample? Do you see it right? A good doctor will have already done that, because doctors will look at data much more than, say, computer scientists. So this is something that you need to do. Again, talk to the experts to know if your data is correct. So Anne-Marie, I think, has another question. I can read it. So it's a one-year student in biotechnology AI. That's correct. BTech is biotechnology. I don't know the acronym. And data science, which all things we have to be done during the 4 years of our biotechnology to get a good job in MNC. I don't know what is MNC. MNC, anyone knows? Kanishka, do you know what is MNC?
Multinational company.
A multinational company.
Big
Sorry,
companies.
this is like an Indian acronym because. Okay, yeah. And as a data expert or AI-related jobs. Okay, I think there are two answers here. So one answer will be do what they want. So learn what they want, which I think is sadly is not the best answer. So for example, they want people that knows deep learning because they have big data. So that's normal. The problem is that big data will be, if you're an expert in deep learning, you are only good to companies that have big data, and this is a small percentage of companies in the world. So you are reducing your possibility to where to work to very few companies. But if you get inside there, you have your life solved. So for that, I will say learn about deep learning, learn about language models, learn about also unsupervised techniques, so basically data mining, learn a bit of search, and learn very well your math, learn very well your statistics, learn about A/B testing and user studies, learn about, let me see, what else will be there? Yeah, I would say that. And for example, what will be my answer? I would say learn about ethics, but they don't care too much about that. Learn about data science, about modeling, about how to use techniques for small data, and so on. So there are two different worlds. One is for 1% of the companies, and the other one is for the rest of the world. So you need to decide if you want to work for the people that is trying to gain more money from other people, or if you want to work for a small company that are trying to do the best for the whole world. So there's like an ethical divide here, and you need to do AI for good or AI for having a good salary. This is your own personal decision. I cannot tell you what you need to do. Pavan asked where we can get data or collection of data in any specific thing for analysis. Well, Google has a beta search engine for data. So I can write that in the chat. So if you don't know it, you should use that. Okay, we'll put it in there. So this is a good place to find data sets for search. So this is the I put the link on the chat. So this is a place where you get millions of data sets to use from. So in some of them, you need to sign a form to download it. Also a place to find data sets, a very good place, one of the best in the world is Kaggle. Maybe many people know because they do competitions where you can win awards. but also it's a place where they share a lot of data. Okay, great. So there you have also the Kaggle URL.
Sir, there was another question, like what are the different applications or softwares which we can start with while doing this analysis and reading such big data and all?
Yeah, there are many basically, let's say, programming environments that you can use to do data science. Some of them, sadly, are tied to a programming language. For example, I think Python is not the best programming language. I don't like the notation of Python. But for example, Jupyter or things like that are one of the best platforms to do data science. So this is one. For example, also you have like R. R is used more in science. It comes more from statistics. That will be another environment where you have your own language. Also, I don't like too much that language. So the sad thing is that there's still not a good combination of a very good programming language with a very good, say, library of functions, but things like Jupyter with Python below and R, and there are others that where you can use are good. So I would say that that's not that relevant. I'm more eclectic on that. When I try to solve something, the first thing is I see if someone has done it before. So don't redo the wheel. So don't reinvent the wheel. So you find something that, for example, in GitHub was done before that is very similar to your problem, and then you have to use whatever is there. So you should be able to be very adaptive and flexible and change from one environment to another. It's also because then you learn the concepts very well. So you know, for example, I know what's an object in many different languages. They have differences, but I know the concept of object. But if you go too deep in one single, say, programming language, you start to diffuse the difference between the concept and the implementation of the concept. And sometimes you believe that things that are true in Python are true in other languages, which are not true. And many times these things are true because someone said, oh, this is funny to do it like this, which was a bad idea. And they do it like that. For example, tuples or in Python have weird things. They're not consistent with other things. So this is some case. So be careful of confusing the concept with the implementation of the concept. One classical example where we are already confused and we don't have anything to do too late, for example, very basic example, maybe you have never thought about this. The people that designed the first file system in the world decided that people should put a name to that file. So whenever we create a file, we put the name, right? And then we have to remember what name we put to that file. And then we start putting letter 1, letter 2, letter 3, letter 4, and then it's impossible to find the letter that you want because you have a generic name. So this is an implementation issue that now is transferred to the concept. Because if I would do it, I would have never asked the user to generate the file name. The file name is something that is an object ID that should be generated by the system. And then if the person wants to find the file, I will give a very good search engine in your computer to find the file. So we shouldn't be putting names to files. But we are already too late. Someone decided this like 50 years ago, and we are confusing the concept of naming an object with putting a file name. And we have many of these examples in computer science where the implementation got basically changed the concept and is part of the concept today. And this is as a design property, design rule is really wrong.
Sir, we have another question by Nirmal. Is there any
Yes.
difference in the usage of big data by data analyst compared to data scientist? The difference between these two job roles?
Yeah, so that's a good question. So I would say that data science is more open, like you can do more things, so you will be able to do the same that the data analyst does. And also depends on how you define these things. So the definition is liquid. It's not, in every country this definition may be different. But my definition is that the data analyst knows a subset of data scientists, so doesn't know so many things, maybe doesn't know about deep learning, doesn't know about natural language processing, but knows very well to understand small data. So will be more small data than big data. And also data analysts need to understand very well the domain of that data. For example, a data analyst will be associated to, say, a bank. That person knows exactly everything that is important for a bank, so understands the problem. So it's more tied to a sector. So I would say data analysts will have, for example, will be a health data analysis, will be a banking data analyst. So you need to be a specialist, because if you don't know everything about data science, you need to at least know what's the data for. So you will be able to understand the data and give insights. For example, you would say, based on this data, I recommend this thing, because he can do the recommendation or she can do the recommendation because it knows very well the data and the problem that it's solving. I think this is the main difference.
Okay, so if any participant does not have any more doubts, we would like to proceed with the vote of thanks.
Kanishka, principal sir has joined. I think we should invite him for speaking a few words.
Yes, sir. Leadership is about making others better as a result of your presence and making sure the impact lasts in your absence. The duty which is conferred upon me today is to introduce the man who needs no introduction. It is a great honor for me to welcome Dr. Mukesh D. Patil sir, the principal of RAIT, who is instrumental in our journey at all times by being a guiding light for all of us and has always encouraged students to give their best. We all look up to him as he inspires us to be a better version of ourselves. Now, I would like to invite our principal sir to say a few words.
Thank you, Kanishka. On behalf of management of the institute and Diva Patil University, I would like to thank Professor Ricardo for accepting the invitation and delivering a talk uh, on this the emerging area. And I am sure that all the students must have enjoyed, and the kind of questions students have asked. From that, I can conclude that students have really enjoyed the talk. Uh, Sir, we wish to have more association with you, and in future also we'll contact you for different activities. So I'm sure that you will accept our invitation and extend your support to our students and our faculty members. So once again, congratulations to RIT ACM for getting this distinguished lecture series and inviting Professor Ricardo and benefiting the students of RIT.
Thank you everybody for the invitation, and have a nice rest of the weekend.
Thank you so much, sir, for your motivating words.
Bye-bye.
If you want to see the rainbow, you got to put up with the rain. I hope all of you found this session insightful. I would like to thank our speaker, Dr. Ricardo Baeza Yates, for enlightening us with your knowledge. Today's session was indeed informative, and I am sure all the participants found it insightful. I would like to take this opportunity to thank the HOD of IT department, Dr. Ashish Jadhav sir, for motivating us in undertaking all initiatives and inspiring us to think beyond success and failure. We are indeed very fortunate to work under your leadership. I'd also like to express my gratitude to the principal of RAIT, Dr. Mukesh D. Patil sir. Thank you to all the students for attending the session. We will be back with more exciting sessions soon. Until then, keep learning and do not forget to subscribe to our YouTube channel for more exciting webinars. Thank you.
Bye-bye.
Thank you so much, sir.
Thank you, sir.
All the participants are requested to fill the attendance and feedback form which has been put in the chat box in order to receive the certificate.